to take a look at a assessment paper looking at the concepts of mechanical energy and also the motion of objects as well. So we're going to start off with a bit of a mixture of the two. So we're looking at archery and the energy transfers involved in that. So what we've got is a diagram showing generally what's happening, and we've got another diagram showing as D increases, what happens to the force. So it says a novice pulls back the string to a displacement of 0.2, but an experienced archer pulls it back further so that displacement is 0.40. And it wants us to suggest an advantage for this extra displacement. So if you stretch a material by a larger amount, that's going to increase the elastic potential energy stored. So that's the first thing I've said there. So this is where the arrow gets its energy from. So if you store more energy in the bow, the arrow is going to leave with a higher kinetic energy, and that's going to mean it's traveling at a higher speed, and it will end up traveling a longer distance before it hits the ground, or will apply a bigger force to the target, something along those lines. Those would all qualify as advantages. So the next one wants us to estimate the elastic energy stored when the displacement is 0.50 there. So a very common answer I saw, I'd say something like 90% of people did this, is they read the displacement off and read the force off and applied half Fx and gave an answer of 37.5 joules, which is completely wrong. So people who've written this have tried to not think about what they're doing, because the equation half Fx only works while the graph is a triangle or while Hooke's law is being obeyed there. So if the displacement was anywhere up to 0.2, that would have been a valid method for solving this problem, but we are no longer obeying Hooke's law, therefore we can no longer use half Fx or half kx squared or any of those equations. We have to use the area under the graph. Work done is the area under a force versus displacement in the direction of the force graph. So the way I do this is I will divide the graph up into shapes so that we can cover most of the area of the graph. So I typically will use either rectangles or triangles, and then essentially all you have to do is work out the area of each of those shapes and add them all together. And when I did that, I got about 80 joules, which is going to be slightly under, so we'd expect it to be slightly higher, but it says estimate, so that should give us a good approximation there. And it's energy, so it's going to be measured in joules. Just a little thing at this point, for those of you who used half Fx, this was a 3-mark question. My question to you would be, what have you done that's worth 3 marks using half Fx? So already in your head, you should be very critical of having done that, because it doesn't really make sense in the context of the amount of marks awarded either. So what we're going to do next is calculate the maximum possible speed when it's released with 58 joules of elastic energy. So first of all, we're going to get a maximum speed if we're doing no work against any resistive forces like air resistance or friction. So that would be the work done is 0. If the work done by external forces is 0, that's going to allow us to apply the conservation of mechanical energy to the system. So let's do that. So essentially, if the work done is 0, if we add together all the changes, that should equal 0 as well, because total energy stays the same. And if we are essentially going to say it's not going to gain any height, so we'll say the change in GP is 0, we can then generate an expression. The initial speed of the arrow is 0, so we can make U equals 0. The final elastic potential energy is going to be 0, because we'll get maximum speed if all of the elastic potential energy is turned into kinetic energy, which leaves us with this expression, half mv squared is equal to the elastic potential energy to start with, which we can then rearrange to make velocity the subject. We want speed, so I'm just going to take the positive root, which comes out as 58 meters per second. So just to highlight a few things, this expression you can see here is the mathematical model of the principle of conservation of mechanical energy that you've learned about. And one thing that occurred to me when I was doing this is actually going, well, actually, if the arrow were to fall, it could actually have higher speed than this because it could increase the final velocity. But clearly in this question, they weren't expecting you to think that in depth about it. But it's just something I thought I'd throw out there because we could have got a higher speed if it decreased its GPE, for example. Okay. Final part of this question, it wants us to state and explain the effect of air resistance on the motion of the arrow after it's been released. So the first thing is to identify the direction of air resistance. So you should know that air resistance acts in the opposite direction to an object's velocity. So that means air resistance will do work to decrease the mechanical energy of a system, and it does it by transferring it to thermal energy, so the surroundings heat up. So the effect of that will be to decrease the final kinetic energy, because remember, at the end, we assumed all mechanical energy became kinetic energy. And that's going to mean if kinetic energy goes down, the speed is going to decrease. So it asked us to state and explain. So this part of the top would be the explaining part, is essentially answering the question, why did that happen? And then the stating essentially answers the question, what happened, the speed would decrease there. So those would be our two parts. Okay, so let's move on to question 2. So we've got a roller coaster set up here, and the car is accelerated to 56 meters per second before it hits the slope. And we've got its mass there, and we've got that it's currently at an angle of 25 degrees to the horizontal, and it wants the component of weight force acting along the slope. Or in another way you may have seen that before, I want the component parallel to the slope. So let's draw our force diagram. So weight force always acts vertically downwards, so you can see that on the diagram. And then what we're going to do is we're going to split the weight force up into 2 perpendicular components, one of which is parallel or along the slope, the other of which is perpendicular to the slope. If the slope is at 25 degrees to the horizontal, that gives us an angle inside that triangle. And if you're not convinced about that, pause the video and work out the angles so you can see that that is 25. So once you've got this triangle, it's a fairly straightforward question. We want the component parallel to the slope, which would be mg sine theta. So we just put mass times 9.81 times sine of 25 gives us the component parallel to the slope, which I've given to 2 significant figures because the angle is given to us to 2 significant figures. Okay, so that's the first part, fairly easy. The next part wants us to calculate the kinetic energy when we've got a speed of 56 meters per second. Again, very straightforward. You're given in a formula booklet the equation for kinetic energy, so there is no excuse for getting this question wrong. Our speed is given to 2 significant figures, so we should give our answer to 2 significant figures, and a number that big should definitely be in standard form. Okay, so we know the initial kinetic energy. Next, what we're going to do is calculate the maximum height that could be reached. So first of all, just like before, we're going to assume there's no work done against resistive forces, or the work done is 0. So what that means is we can apply conservation of mechanical energy again, so same as before. So we're not going to think about elastic potential energy here because we want the maximum height that we can reach. So essentially, if we add together the change in GP and the change in kinetic energy, that should be equal to 0. So V stands for the final speed, U stands for the initial speed. At maximum height, the smallest the speed could possibly be is 0. So what that's going to mean is V is 0. So we can put that into our equation. We can cancel out the masses, we can cancel out the minus signs, and we can rearrange to give us an expression for the change in height, which we would give to 2 significant figures because the 56 is a 2 significant figure number there. Okay, so that's the theoretical maximum speed if all of the kinetic energy were to be transferred into GP. So next, what we're going to do is explain why it doesn't reach this height. So I'm going to do this the same way as force. So our resistive forces are going to act against the motion of it. So they're going to act to decrease the mechanical energy by transferring it to thermal energy. So what we've done is we've explained why. So therefore, what would happen is we'd expect the maximum height to decrease because our final GP is smaller. But the thing I'd highlight here is it did not say state what happens, it just said explain what happens. So actually we don't even need that second part here. It would just be the first part. It only said explain. Okay, so the final question on this part anyway is if we start at a height 140 and only 87% of its energy is converted to kinetic energy, what will be its final speed? So I've started with the expression the final kinetic energy is 0.87 the initial GPE. I've put in the equations for that. You'll notice the masses cancel out again. Rearranged to make the speed the subject. I've taken the positive square root because we just want speed and given it to two significant figures because the 87% is a two significant figure number there. Fairly easy. Okay, so let's move on to question 6. So this one's looking more at relationships between different properties. So we've got that the skidding distance is directly proportional to the velocity, or d equals kv. That's what that equation tells you. And we've been given some values, so we know that when d is 45, v is 30, and we want to know d when v is 15. So our first thing to do is going to be working out what k is, because we don't know. So that's what I've done. I worked out k, and it's 1.5 seconds would be the unit there. So once we know k, we can use our equation again, put in our v equals 15, and that gives us d is 22.5, but giving it as 23 would be an appropriate number of significant figures. So that's just a bit of relationships there. We've got a mass of it, and we want to find out what the average skidding force would be to stop the car from 30 meters per second in a distance of 45 meters. So I'm going to do this using conservation of energy. So the work done by the skidding force must be equal to the change in kinetic energy. We can't change energy without doing work. And when it stops, the final speed will be 0. So we can get an expression for the work done by the force. Work done would be the average force times by the distance. So we can essentially get an expression for the average force is the work done divided by the distance. So I've used my expression for work done divided by the distance, substituted the numbers in, and we get an average velocity of minus 7,000 newtons because it's acting against the motion of the object. So it should be negative, and two significant figures because the 30 and the 45 are both given to two significant figures. So that will be the average force. So by considering the equations for kinetic energy and skidding distance, discuss how the heat generated is related to d. So what it wants is a relationship between d and the thermal energy. So is it directly proportional, inversely proportional, etc., that kind of thing. So we know the work done by our force is going to be equal to the thermal energy, and we know the magnitude of the work done is equal to the kinetic energy there. So what that tells us is that thermal energy is going to be directly proportional to v squared, because essentially thermal energy and kinetic energy will be equal to each other, but with different signs. We know from the equation earlier that d is directly proportional to v, which means d squared is going to be directly proportional to v squared. So putting those two things together, we're going to see that thermal energy and d squared are both directly proportional to v squared, so thermal energy is directly proportional to d squared. That would be how they are related to each other. That's what that means. Okay, so this next question, we're going to do a bit of two-dimensional motion or projectile motion. So we've got a scenario and we've got some velocities, times, and some distances, and it wants us to show that the ball takes 0.6 seconds to reach the net after being served. So I'm going to write out the different properties of motion. So Firstly, in the vertical direction, when it reaches the net, it's going to have gone down 1.5 meters. Its initial speed in the vertical direction is 0 because it says it's traveling horizontally to start with. We don't know its final velocity, so I haven't got that there, but we know its vertical acceleration is 9.81 downwards, so it's minus 9.81. We can do the same thing in the horizontal. We don't know how far it's gone yet, but we know the acceleration in the horizontal direction is 0, so the starting and the final speed would both be 18, but again, we don't know how long it takes. So what we're going to do is we're going to use the vertical properties to work out the time. And as to why, if we look at the horizontal direction, we can see because we don't have displacement, the only equation we could use is v equals u plus at. But since a is 0, that just leaves us with an expression v equals u, which is not helpful for finding the time. So we must be using the vertical direction, which we always do to find the time. So we want to find time, but we don't have v, so that tells us we're going to use s equals ut plus half at squared, but u equals 0, so we can simplify it. We rearrange to make time the subject. We take the positive square root because time is a scalar. We put our values in and we get a time of 0.5548, which is roughly 0.6. And it is important you show your unrounded answer first to show you've done the calculation correctly before you round it off to the final answer. So that's the time. Next, we want the vertical component, the velocity, as it passes over the net. So we now know what the time is. So you can see I've added that into the Suvat expressions there. We want in the vertical direction. So I'm not even going to use that new time we've just figured out. So I'm going to use v squared is u squared plus 2as. Again, u is 0. Substitute our numbers in and we get a final velocity of 5.4 meters per second to 2 significant figures there as our answer. Okay, so that's our final speed. What it wants to do is work out the overall velocity of the ball. So we need to remember that velocity has magnitude and direction, so we're going to need both. So I'm going to start by drawing myself a diagram of the motion of the ball when it passes over the net. So that's what we've got, and I've labelled an angle in there theta. So first of all, to calculate the magnitude, we're just going to use Pythagoras because those two sides are perpendicular to each other. So it doesn't matter that the velocity is negative because it's getting squared anyway, but that gives us a velocity of 19 meters per second to 2 significant figures there. Then if we do this one to work out the angle, I'm just going to use tan because we have the opposite and the adjacent side. Again, plug our numbers in. Our answer is going to be 17 degrees, more minus 17 degrees, which means it's 17 degrees below the horizontal. So we've got its magnitude and direction, so we are describing the velocity of the object. Okay, so moving on to the next question. This is the last question in this paper, and this is by far the easiest question in the whole of the exam. So realistically, those of you with good exam technique, you should be doing this question first, having gone through the paper and seen that this is really easy. So let's start off with this. So state the difference between a scalar and a vector quantity. So scalar quantities only have magnitude, whereas vector quantities like velocity just now have both magnitude and direction. That's the key definition that you need to know. It wants 2 examples of each. You could have picked from loads that you may have come across already. So things like displacement, velocity, acceleration, force. Momentum also would be vectors, and distance, speed, time, mass, volume, density, energy would all be examples of scalars. You'll come across more as we go through the course, but that's basically what we need. So we've been given a scenario of a ship with a sail, and we can see the force from the wind is acting at an angle there. So it tells us the force is 2.8 kilonewtons at an angle of 35, and it wants the 2 components. So my first thing to do would be draw those 2 components. on there, so on the diagram, so you can see them. So the horizontal is going to be cosine, the vertical is going to be sine. So that's what we can do there, making sure our calculator is in degrees, not radians, of course. And if I put in F is 2.8, that's going to give me an answer in kilonewtons. Do the same thing for the horizontal direction, and we've resolved it into two components. The last part of this wants us to work out what the power is from the wind. So we have an equation that allows us to do that, P equals FV. So important thing to know about P equals FV is that the force and the velocity must be parallel to each other, which means we need to be using the horizontal component of the force in this equation because that's the direction the velocity is horizontal. So once we've established that, I've put in the force in kilonewtons, so I get an answer out in kilowatts, which is what we were looking for in what we could give in this question. We could have obviously given it as 19,000 watts, but this is a good enough answer. Okay, so that finishes this video looking at this assessment. I hope you found that useful to review and improve your knowledge of these topics and have a look at some of the exam technique for it. If you have any questions, please feel free to comment on the video and ask. I'd be more than happy to get back to you about it. And thank you very much for taking the time to watch.